Hi class. Okay, so I got the camera working. So I want to follow up on something I briefly mentioned in class, which is that sometimes it's necessary to transform and standardize these statistics. So what do I mean by that? What I mean is the most important part of the exercise or of calculating these things isn't the computation, and it's not even knowing the names, it's how to interpret them and how to make sense of the information. So, because like I keep saying, right, any machine can do this. It's not really the important part, although you should know how to do it. What does it mean? All right. So, I talked about in class part of the problem with calculating variance using the example of the test, right? So, if you go back to your slides, you'll see there's an example where you give a test to one class, everybody gets 100 or a 0, and the other class gets either 52 or 48. So, in other words, everybody is either 50 above the mean or 50 above or below the mean, and the other test it's 2 above or below the mean. So obviously the first test is going to have a lot more variance, or that class has a lot more variance than the second one. So when you compare the two variances, you can see one is bigger than the other. So all right, that tells you one is more variance, more spread than the other. But in and of themselves, the variances don't mean anything or mean very little. So for example, the first variance is 2500 and the second variance is 4. If you only have one sample and you look at that 2500 variance, all right, that's good to know. It's helpful, but ultimately it doesn't tell you anything. So part of the advantage of standard deviation is that when you take the square root, it returns your measure back into its original units. It's a lot more interpretable. So taking that sort of thinking, keeping in the forefront of your head that really the interpretation of the statistics is just as important as calculating them. And like I actually said, more important than calculating them, we have a sort of a similar problem with skew and kurtosis. Right? Everything is raised out to the third or the fourth power when calculating those two things, so the units effectively become meaningless. In fact, when you look in a lot of sources, they effectively say that they don't have units, which is true, for all intents and purposes. So then what really are you measuring? So I did mention in class that kurtosis, if it's above, below, or equal to 3, it has some interpretation, but I said that the way we were doing it, where you just take everything to the fourth power and then average, that won't really sort of return for you that clean comparison. You're going to do some work and that I would have to talk about later because we're running out of time. So that's what this video is doing. So there's basically two steps to get there. The first is I'm going to talk about transforming your sample, right? And the variables in your sample. And I'll be talking about how you can use transforming these variables to standardize them and then sort of recompute all the statistics, the mean, the variance, the skew, and the kurtosis in a more easy to understand, easy to work with fashion. Okay, so what you're going to do is first think about transforming your variable. So here's what I mean by that. So I think you can see up on the board, and you know what, I'm going to shade this in so it's a little bit clearer. Oops, a little bit easier to see. This is not working out quite the plan. Alright, one second. I had the cap on for a while, so the pencil dry. Alright, anyway. So, great. Okay, so I think that is easy to see. Okay, so you have some random variable x, and what I mean by that is that you take some sample, and each element in your sample you can index as xi, right? And I is between, say, 1 to n. So, looking at the worksheets I gave you, for example, I had something where it was like 4, 8, 4, 1, 2, 4, blah, 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 blah. So you have one of these, each element is an xi, right? So this is x1, x2, x3, x4, etc. And collectively, I can just refer to one of these samples as x, all right? Now let's say what I wanted to do was take every element in x, each one of these, and I wanted to change it. So let's say I wanted to add 2 to all these. And then what I wanted to do was multiply them by some number. So this is what I mean by a transformation. So you can see I've written here on the board y equals a plus bx. And what this is saying is that you can transform any of these samples by doing a linear function like this, a linear transformation. And it turns out you can still have a really easy way of figuring out what the mean and the variance and other things are even after you do a transformation. So the first thing that you might want to know is, let's say you do some function like that, right? Like, let's say that first I multiply every value in my sample by b, and then I add some number a to it. All right, so what happens to the mean? So it turns out you can use some really simple properties from algebra to figure out what the new values would look like, what the new statistics would look like. Okay, so first off, I want to calculate the mean. So I want to know the mean of y. So y bar, let me see if the blank pen is working now. So I have y bar. So y bar is equal to 1 over n, sum of I equals 1 to n of yi, of all the yi's, which is equal to 1 over n, sum I equals 1 to n over a plus b xi. Okay. So hopefully everybody can see me having written this out and it's clear. So what I'm gonna do is show you how to transform this. So remember that a and b are constants, okay? So when you distribute a summation sign across constants, it's gonna look like this. So like 1 over n times na, right? Because when you sum a constant n times, it's just going to be n times a, plus b 1 over n sum 1 to n of the xi's, right? Because when you have a constant times a variable with the summation sign, you can just pull out that constant. Okay? So going back to here, the n's cancel out, you just have the a plus b x bar, right? Because here's my average right here. So y bar is equal to a plus b x bar. So you can see here that when you do a transformation on one of the variables, right, on your sample, if you add some constant to all the numbers, or you multiply the numbers by some other constant, and then add some linear transformation like that, you can pretty easily back out what the new mean would be just using algebra. All right? And it's the same thing with the variance. So we'll leave this up here, and if you need to see this, it's going to be both in that moments group of slides that are on EEE, and you can look at it here on the video. So for variance, it's a similar operation, or similar style thinking. So if I want to compute the variance of y, that's going to be equal to 1 over n summation I equals 1 to n of yi minus y bar squared. Okay? So the first thing now to solve this, what I'm going to do is substitute in the formula for yi, right? And for y bar. So it's going to become a plus b xi minus a, in parentheses, a plus b x bar. The whole thing's squared. Okay, so hopefully everybody can see that. So if you notice, we distributed this negative sign, the a's cancel out. And this is going to become 1 over n summation I equals 1 to n of b xi minus b x bar squared. Okay? So you can pull out this b, right? You can factor out the b. So this is going to become b squared times xi minus x bar squared. Well, we know what that is. That's just equal to the original variance. So the variance of y is equal to b squared times sigma squared, or the variance, or better put, the variance of x. Okay. So the point of this exercise, and this is completely fair game on the midterm, and trust me, I will be asking questions about this kind of thing, is that consistent linear changes to your sample, whatever they might be, you can still very easily figure out what the new statistics will look like just using basic properties of algebra. So what's the point of this? Well, the point of this is that there are going to be some cases where it's really useful to be able to take a random variable or take a sample, do one of these transformations on it, and then use that transformed sample to explore new properties and new ideas. So for example, the most common thing you'll see is that with a sample, you will standardize it by having it so the new sample has a mean equal to 0 and a variance equal to 1. And it'll be clear later into the class why this has a lot of desirable properties. But just for now, I want to show you what that transformation looks like. So what you can do is this. So let's say that instead of defining yi is equal to a plus bxi, if I define yi as being equal to x I minus x bar over the standard deviation, it turns out that this transformation has a mean equal to 0 and a variance equal to 1, and that's really handy. And like I said, you will see, like, it'll become very clear later just how important this transformation is, but just know for now, and again, it's in the slides, that when you change your sample that way and do this transformation, the variance of yi is now equal to 1, and y bar is now equal to 0. Okay? So, it turns out that this has consequences, particularly for the kurtosis. So if you go back and you look through your slides, especially the moment slides, I start the section on transforming and standardizing variables in slide 30 in the moments PowerPoint. So you're looking through that and you'll see that that starting with slide 31 and going forward, I show how to do these linear transformations. And then around slide 34, I talk about standardizing them. And standardizing them just means changing it so that the mean is equal to 0 and the standard deviation, the variance, is equal to 1. All right, and I do a little proof in slide 36. No. I explain in more detail about how the mean is not equal to 0. And I show what happens when you standardize, and the same thing with the variance, and how it becomes equal to 1. Now, starting around slide 40, this is when I talk about what the implications are for the skew and the kurtosis. All right? And the reason you can only see half me right now is because I'm flipping through my PowerPoint while looking at a different screen. And I'll get back to the whiteboard here in just a second, all right? Don't worry. Okay. All right. So now doing the same thing, or with the same idea in mind, what I want to do is see what this means for this process means for the kurtosis and the skew. All right. So it turns out, a nice property of the skew and the kurtosis is that they already have the means different out, right? Like, so with my yi here, I'm differencing out the mean. Well, the skew and the kurtosis are already calculated that way, right? Like they're already the third and the fourth moment about the mean. All right. So to do the full adjustment, what we do is that we now calculate the skew. The standardized skew is of x. It's going to be equal to, and you can see this on slide 40. It's going to be equal to 1 over n to n of xi minus x bar to the third. And then you're going to divide it by finding that second moment, or in this case the variance. It's the second moment to the 3 halves. Okay? And you can see for yourself that this is it's following the same idea. It's the same algebra that underpins this as in the standardization that resets everything to have the mean equal to 0 and the variance equal to 1. So when you do this, it just makes it a little bit easier to work with. And there's sort of an arbitrary rule of thumb that you can follow. So there aren't, unlike the kurtosis, there isn't sort of a universally accepted rule on how to interpret it. You'll see different things in different places. But the rule of thumb that I most often follow is that if this calculation yields something greater than 1 in absolute terms, then you have a significant problem of asymmetry. Your distribution is being pulled in a very important, in a meaningful way towards one tail or another. So just as a comment though, because I don't think I mentioned this in class, so this is important, is that part of the interpretation here with the skew, even when you standardize it, the most important thing you want to be paying attention to is the sign, right? So because it's raised to the third, it can be positive, negative, or 0. If it's 0, it means that the distribution is perfectly symmetric. And if it's positive, it means that there's more, in a relative comparison, right? Like there's more values in the right tail, right? There are more extreme values out towards the right tail. The distribution is asymmetric towards the right tail. And if it's negative, it means the opposite, right? Like there's more asymmetry, there's greater outliers in a relative way towards the left tail, right? Because if you think about it, because this is being taken to the cube, not only does it mean that it can be positive or negative, it means that deviations away from the mean towards, say, the left tail are going to be increasingly negative the farther they go in sort of a non-linear way, right? When something is 200 below the mean and it's being raised to the third, it's going to be a pretty big number, even when you average it out. All right? So likewise, with the kurtosis, you can standardize the kurtosis of x by finding 1 over n, taking that fourth moment, right? So xi minus x bar to the fourth, and now what you're doing is dividing by the variance squared, right? Sigma to the fourth, but you can call it just the variance squared. Okay? So what this does what this does is now we can do that comparison to, having 3 as our benchmark that I talked about in the previous class and in the slides. And where that comes from is that the distribution that I think I've mentioned a few times and it's become very prominent in the rest of the class, and you'll use it in 15b and you'll use it all the time in econometrics, is the normal distribution. Don't worry if you don't know what I'm talking about, it's just something that'll become very clear in a little bit. And the normal distribution is used so often across so many different fields that when we calculate kurtosis and we're standardizing it, what we're effectively going to do is compare it to the normal distribution used as our benchmark. So when this standardized kurtosis is less than 3, what that means is that it's flat, right? Like there's a lot of action in the tails, a lot of the extreme outlier, a lot of the variance is being driven by extreme outliers. It's platykurtotic. And when it's equal to 3, this calculation here, it's mesokurtotic. And when it's greater than 3, it's leptokurtotic. So where 3 comes from is that 3 is the kurtosis, the standardized kurtosis of the normal distribution, the standard normal distribution. So that's where the benchmark comes from, that's where the interpretation comes from. Effectively, we are making sense of this statistic by choosing this normal distribution that I've mentioned as our benchmark. Don't worry if that doesn't make 100% sense just yet. Just sort of follow the idea that I'm trying to make here, where ultimately we're calculating these things, interpretation is important, here's how we interpret it, here's how we make sense of the interpretation, right? Once again, for skew, we're looking at, is the standardized skew positive, is it 0, is it negative? It is also possible for it to be undefined or infinite, but don't worry about that for this class. And again, if it's positive, it's out towards the right tail. It's where the asymmetry is being driven by. If it's 0, it's symmetric. And if it's negative, it's from the left tail. The left tail is fatter. Alright, and kurtosis, again, it's in your slides, whether it's platykurtotic, mesokurtotic, or leptokurtotic. Alright, it's all whether this calculation comes out to be 3. Okay, so that's the idea. We can take a sample, we can do transformations on it. A lot of the properties of the sample will be preserved even after transformation. We can use some basic algebra to figure out what the new statistics will look like even after transformation. And one of the advantages of transformation is that once we've done it, we can then make a little bit more sense of our statistics, especially our higher order statistics, than we could before. So collectively, what you're now going to be able to do after this unit is take a data set, distill it down to some subset of statistics, some descriptive statistics, some ideas about the central tendency of the data are, and it will give you a lot more information about what that data set contains than you did just from staring at it blankly or doing a simple mean, right? I hope that if you get anything out of this, it's that you have some choices about how to describe your data. You don't need to use all of them, although they are helpful. And I hope that you are now thinking more broadly about how to describe data than just like the most simple thing of taking a graph and reporting the average, right? I hope, really you can if you're convinced of one thing, it's that an average is often not enough. You're often better off and you're doing a better job of clarifying the reality by providing more information. Okay. Email me if you have any questions. Hope you guys have a good night.